Here I'll go through an example in 6.1 of a one-sided hypothesis test. In this example, there's an engine and it emits 100 milligrams per second of nitrous oxide, which is a pollutant, so we'd like to reduce this. So they come up with some new design or some modification to the engine, and they say that they'll use the new design if they can show that the new design has less than 100 milligrams per second of this pollutant. So we'd like to show that it's less. So the thing that we want to disprove then, we assume that after the modification, it's the same. So mu is greater or equal to 100. This is the thing we'd like to show that is false. Then, in contrast, the alternative hypothesis, if mu is not greater or equal to than 100, mu must be strictly less than 100. So this is what the engineers would like to know, because if we can show this, then we can show that the engine pollutes less, and so we'll make this modification. So they do an experiment, and they get x bar is equal to 92 milligrams per second with sample standard deviation. Sigma is approximately S, which equals the standard deviation is 21 milligrams per second. So the question is, can we, now we frame this in the terms of hypothesis testing. First of all, if there were no standard deviation, if the standard deviation was 0, if we were perfectly sure, if we had perfect measurement somehow, no noise at all in our data or our experiment, then we could just conclude that now the new mean is 92 milligrams per second. But this 21 milligrams per second means that we got a bunch of data that were not exactly 92, like some were much higher, some were much lower, and we don't exactly know what's going on. So that's why we need the hypothesis test. Now we can take a look at the probability density function for x bar if mu is actually equal to 100. So this is within the null hypothesis. Setting mu equal to 100 is as close as we can get to saying that mu is strictly less than 100. So it could be anything at all greater than 100, but we choose the one that is as close as it can possibly be to the alternative hypothesis. So in this case, 100 is our mean here, and then we observed an actual value of 92. To compute the p-value, we just find the area to the left of this 92, okay? So we're looking at, we have this PDF that we're looking at, so this is distributed as normal 100, and I forgot to say that it measures 50 engines. So the distribution under the null hypothesis, it has mean 100, standard deviation, squared standard deviation of variance 21 squared over 50. Okay, so now we just need to find the area over here to the left-hand side, and that will be the p-value. there are two ways to do this. We could just plug it in directly. So the first way, which I think is the more straightforward way, is to just look at the probability to the left of there. So that is, in R, you can do P norm of 92 for a distribution that has mean 100, and standard deviation should be equal to 21 over the square root of 50, okay? The square root of the variance. You plug this in, you get 0.00353. So this is the p-value. The second way is to convert to z-score and use a z-table. So to convert to a z-score, you take the mean, you take your value, 92, minus the mean, divided by the standard deviation, 21. So our z-score is equal to this, 21 over square root of 50. So this is approximately negative 2.69. Now you take this number and look it up in the z-table and figure out what the equivalent area to the left is. Okay, look up in z-table. Look up the probability that z is less than that, and you'll see it's about the same thing, 0.0036. Although, of course, the direct way of doing it without rounding is more precise in R. So anyway, there's both two ways to do it, and that's it. That's how you get the p-value. And that's how you phrase the hypothesis testing with the null and the alternative hypothesis.